Now, subduction is about 6 centimeters per year. It's slowing down a bit as we get closer to the pole of rotation, 5 centimeters per year up in the northern part of Sumatra, but highly oblique. And this oblique subduction causes a number of problems, which we will briefly touch on. The main thing that happens is there's a giant strike-slip fault, enters or starts down here in the accretionary prism, goes out to the trench, comes up through the western side of Sumatra, goes all the way up and exits out here, the north side of Sumatra. So this entire block between the Sumatra Fault and the trench is moving to the northwest. So it is just a few millimeters per year, but enough over the millions of years that it's been going on to have lots of offset along this Great Sumatran or Semangko Fault. Offshore, there are many fracture zones that cause sediment that has been coming down in from the north, filling up the Nicobar fan. Once that sediment hits these fracture zones, it's difficult for it to maneuver over towards the trench. So the trench is still funneling sediment down along here, and we'll see some seismic profiles through this area that show us the sediment in the trench that's being accreted. At this point, we start to see islands forming on top of the accretionary prism. Simalui Island here, Nias here, and some other ones up to the north. So this island is called Siberut, and I'm going to show you next some seismic profiles in this area. So this is going north from southern part of Sumatra up towards the central area. So this is the southernmost profile, middle one, and the upper one. These are just line drawings of the line drawing interpretations of these industry seismic profiles. We can see there are a number of well-developed thrust faults down at the toe of the slope. The thickness of the accretionary prism is increasing as we go landward. Sediment initially is stripped off of the descending plate. Plate motion, relative plate motion is this way. This material, there are thrust faults that are smashing this trench sediment and building up this large accretionary wedge or accretionary prism. So by this time, up to the fore-arc high or outer arc ridge, the width of this accretionary prism is now about 90 kilometers. So we've gone in the south from about 40 kilometers through 60, and now it's getting as much as 90 kilometers wide. The other thing that's of interest here is sediment is managing to get past the outer arc ridge, which is just back here. There are canyons that are coming through, there's sediment slumping off and filling up these little depressions or trench slope basins. Now on Nias Island, where we were doing our sediment mapping and structural mapping, there are equivalent of these sediments that are laying on top of the accreted material. Accreted material is Oligocene and older. The slope sediments are Miocene and younger. They show now they are up at sea level The oldest sediments were initially deposited down in little small basins at the toe of the slope in water depths that were too deep for calcareous nanofossils and microfossils, so they're only radiolarians. As we go up the slope in these basins, they get shallower and shallower, and the stratigraphic section on gneiss showed exactly the same thing, sitting on top of the accreted material, deep water sediments. As they get jacked up higher and higher and higher, the sedimentation is happening at shallower and shallower levels. So again, here, big thrust faults still actively deforming within the accretionary prism. So those three profiles were down here. The previous ones, we've been marching up through southern Sumatra, and now we're looking at this accretionary wedge, now with islands poking up above sea level, 90 kilometers or so up to the top of this ridge. Gneiss Island is right here. And I'm going to show you some fairly recent, within the last 20 years, seismic lines that were collected by an industry group. Before we went to gneiss in the 1970s, there were a number of exploration wells that were drilled up to the shallow water here, all the way around in the shallow areas. It was well known that there were Miocene carbonates, Miocene reefs, that the companies thought there might be petroleum reserves in those reefs. They drilled a couple shallow wells and decided that it was not really very good place to do prospecting. So another company came in, as I said, about now, I think it was 10 to 15 years ago, with a much more powerful system, and was able to image the area around gneiss. Let's see, sorry. So we're going to first look at this line that's well south of gneiss in this structural high that goes across the entire forearc basin. Here, south end of gneiss, and another one up the northern end of gneiss. So here is an enormous amount of material, 0 to 5 seconds at this point. The descending oceanic plate is down here, probably about 10 kilometers deep. So we have almost 10 kilometers of material built up in this accretionary prism. It's highly deformed, being thrust up, very steeply dipping thrusts that are very hard to image. Up on gneiss, we were able to see some of this material, and I'll tell you a bit about that in a few minutes. But here we can see strong basement that turns out to be Mesozoic, coming down here, Paleogene, he says. Some of the older material down deeper gets into the Mesozoic. Sediment filling up the basin and basically thrusting back towards Sumatra. So here's the next line that's a little bit closer to gneiss. We have this very strong unconformity coming along this way. These are, in fact, older carbonates sitting on top of basement. So the whole region has subsided probably about 3 kilometers here. There was an old shelf break, and then off to the edge of the where the initial subduction was happening. All of these sediments are onlapping in this forearc basin, widening the basin. Up here, this profile is adjacent to gneiss on the north side. There's a little map right here. So here's where this map is. Here's gneiss down here. We can see Again, probably about 6 to 7 kilometers of sediment and strongly deformed material inside here, just thrust faulted completely. This is another line that goes right along the edge of gneiss. Again, we see this very strong unconformity down here, sediments building up inside. There always, or there has been since the early part of the tertiary, there's been a ridge over here, an accretionary prism, ponding sediments behind. But we can see lots of very recent deformation as the accretionary prism itself continues to get squished up towards Sumatra, uplifting this outer arc ridge. And this, as I said, comes right to the edge of gneiss. We did a number of transects across here, and we could see melange zones about where these lines are. Those are zones of melange, probably in this area where the oceanic sediments have been strongly deformed and accreted in thrust faults, thrust packages with younger sediments deposited on top of them, starting out being deposited in very deep water in the whole region as material is shoving underneath the islands, uplifting it. They get shallower and shallower. So those lines that I just showed you are down in here. There were 3 of them down here south of gneiss. The lines at gneiss were here. And now I'm going to show you 3 more lines as we get further up into Sumatra, or off the west coast of Sumatra.